Yeah, it's I don't know, it's just like a nice thing to have, and I hope I get it again, but
Well, I will.
I hope I get it this next time.
I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, I thank you for these students. Just ask you to guide our work today, Lord. In your name I pray, Lord Jesus. Amen. So I'm a little bit apprehensive about whether or not I really should cover this chapter, because I have this sneaking suspicion that the details I'm going to skip in the next chapter may be based on the details I'm covering right now, but probably best if we spend at least some time on chapter 5. So my apologies if this is kind of a mathematical cul-de-sac here, so to speak. And I don't remember how much this is needed into the later parts of the course. So anyway, so we're in chapter 5 of Erdmann and Wilden. Yowzers. Erdmann and Wilden. And these are basically preparing us for the statement of Lee's and Engel's theorem, which I do hope to state today. And okay, so anyway, let's get right into it. Lemma 5.1. It says, let X be an element of L. L is a Lie algebra here. If X, I'm sorry, I have buried the lead here. So this whole chapter, right, is about subalgebras of GLV. So here, V is a n-dimensional vector space over the field F, and we're letting L be a subalgebra of GLV. So I probably should actually say that. So V, n-dimensional over the field, which we'll probably think of as reals or complexes, and L, subalgebra of GLV. All right, now here, that's the context we find this lemma 5.1. Let X be an element of L. All right, and if the linear map X from V to V is nilpotent, then add X is nilpotent. All right. So you haven't missed anything, Audric? Okay. So proof here, he says take Y in L and expand the adjoint. So if you, his proof is basically by formula. If we look at the mth power of the adjoint of X acting on Y, then we're looking at like a nested X with X with XY, like that. And he says every term in the resulting sum is of the form. So terms of form x to the power j, y, x to the m minus j. All right, for some j between 0 and m. All right. So let's see here. Oh, okay, so like the net degree of the x's here is always m, right? I mean, he gives the specific formula for m equals 2 here. He says, suppose where would I lost it? Suppose that x to the r is equal to 0. So why can we assume that? That's what it means for, yeah, that's what it means for x to be nilpotent. It means that if we compose it with itself enough times, we get 0. Right? So if we look at m greater than or equal to 2r here, right? See what that does? That means if you look at x to the j, y, x to the m minus j, if you look at this condition, that forces either this or that to be at least degree r. So like if j is greater than r, then that's 0, right? If j is less than r, then m minus j is greater than r. So any way you slice it, you're looking at the composite of x at least r-fold times. Consequently, since that happens for every term in the nested commutator that we're facing here, it implies that, you know, the adjoint of x to the m is equal to 0 for such m, which is to say that the adjoint is nilpotent. That's a bold calculation right there. That's what that is. I like it though. I like it. All right, now the next section, it sometimes blows my mind. This concept of weights, it's a sort of a generalization of the idea of eigenvalues. All right, so now you talk about eigenvalues. What do you talk about them for? So typically we talk about eigenvalues. We have a fixed linear transformation, right? And we talk about the eigenvalues for a linear transformation. So what they explain in this section is that we're now generalizing the notion to a family of linear maps. And we want to talk about an eigenvector for a whole subalgebra of GLV. So let A be a subalgebra. So just like L was in lemma 5.1, okay? He wants to say V is an eigenvector for A. V is eigenvector for A. What's that mean? If V is eigenvector for all, let's say, little a and A. And he gives a more precise accounting for what we mean by that. He means in particular that, A of V is an element of the span of V for all A and A. So he's not saying that the eigenvalue, he's not saying that the eigenvector has the same eigenvalue for every operator in A. It's like this eigenvector could have different eigenvalues for different operators in the subalgebra. But it is a common eigenvector to the totality of the algebra. Right? So, and he gives an example that's pretty easy to understand, like diagonal matrices. Then the standard basis is an eigenvector for A. Like that's his first example. It's pretty easy to understand. It's probably worth writing out. So example 1 here. If you let A equal to the diagonal, n by n matrices, then of course A EI is an element of the span of EI, right? For all A, well, let me say little a, for all A in A. So that would make the standard basis, each one of those would be an eigenvector for the diagonal matrices. Let's see here. Now, he says it's not so obvious how we should generalize eigenvalues. I mean, if we look at this example that we just did, he says the eigenvalue of A on EI is alpha I, but this varies as A runs through the elements of A. So we must be prepared, he says, to let different elements of A act with different eigenvalues. Agreed. We can specify different eigenvalues of elements of A by giving a function, lambda, that goes from A to F. So, all right. He says we're going to specify eigenvalues of elements of A by lambda, which is going to be a function from A to the field. All right? He says the corresponding eigenspace, V lambda, is going to be, what is it going to be? V and V, such that what? Such that A of V is equal to lambda of A times V for all A in A. So then his exercise 5.1 is to check that these eigenspaces are indeed vector subspaces of V. And then part 2, to use the notation to basically look at the dual basis to the, well, what's he doing here? I guess the dual basis to the standard basis and show that it gives you something here. All right. So he says let V be in V lambda non-zero A and B and A, alpha and beta and F. All right. So we should consider well, we can move to the other room now if we want. The giggling will subside soon. All right, so he's like, consider V an element of V lambda and A comma B in the algebra that we're looking at, and alpha and beta scalars in the field. All right. Then this is kind of an important calculation, I think. Let's go through it here. Alpha A plus beta B, so that's an operator acting on the vector V. Okay, so that is going to be equal to alpha A acting on V plus beta B acting on V. All right. But since V is in V lambda, that means that the eigenvalue for V with respect to A is given by lambda of A times V, right? And likewise over here, lambda of b times v. And then what? Well, then we can factor the v out, and we get alpha lambda of a plus beta lambda of b all times v. All right. He says, so the eigenvalue of alpha a plus beta b on v is what we have pictured there in the parentheses. So let's see here. Eigenvalue of this operator is that. And what's the larger point here? Since this holds for all v, what does that tell us? So this, I mean, this is by definition lambda of alpha a plus beta b acting on v, all right? This is the, you know, whatever is the number that appears in front of v is the eigenvalue. So since that holds for all v, that tells us that in fact lambda of alpha a plus beta b is equal to lambda alpha lambda of a plus beta lambda of b, and that is telling us what about lambda? Yeah, this function is not just any old function from a to f, it's a linear function, right? So therefore lambda is in fact an element of the dual to a. Right? It's in a dual in the sense of it's a, you know, it's a linear map. I forget what our I don't know what our notation is in here for that, but I usually use something like linear map from A to the field, but you know, notation varies. Some people might say hom over f, A to f, something like that. I mean, there's various notations. It's a linear map. It's a dual vector. And that brings us to some standard terminology. Now that we have proved these things are, you know, what they are, if I can find my juice. Yeah, Audric, I was glancing through Dr. Misra's notes, and it does look quite different than this book, doesn't it?
Yes.
It's funny because Bill's like, oh, it's the same. And, you know, it's, I got to remember who I'm talking. I got to remember who I'm talking to.
Definitely answer stuff, but you don't come to the nice, like the way he set up his homework. He has nicer ways. Like he set up the question as if you read Mr. Snow's, if you read.
Oh yes, those notes. Absolutely. That's because, yeah, Bill was teaching out of Misra's notes. And, you know, like I said, as much as tempting as that is, and if I had more time for this course, I'd be more inclined to do it. Because Dr. Misra's notes are very, what's the word? Relaxed, right? I mean, there's a lot of like careful development in those notes. They're wonderful. But they're also unpublished. Which is at odds with some of my larger goals for this long term, you know. Anyway, definition here, a weight for a Lie subalgebra. A of GLV, all right, is a linear map lambda from A to F, in other words, a dual vector, such that v lambda equal to v and v, such that a of v is equal to lambda of a times v for all a and a, is a non-zero subspace of V. The vector space V lambda is the weight space associated to the weight lambda. Thus, V lambda is non-zero if and only if V contains a common eigenvector for the elements of A, and the eigenvalues of the elements of A are given by the function at lambda. All right. Now it starts to... So basically, the difference between the start of the section and the end of the section is just like we proved linearity, and now he's giving the honest to goodness definition of this thing, right? Like, in a faster book, they might have just said, it can be shown that this definition makes sense, and just plopped it down, you know? Dr. Miser probably spends 10 pages developing this. You know, like
I have it with me. If you ever need me to check it.
What's that?
I have it with me if you need me to check it.
No, I have it. I just, I brought it in case you had questions. But let's see here. So exercise 5.2, he's got the upper triangular matrices. He says, show E1 is an eigenvector for A and find the corresponding weight and determine its weight space. I say we work exercise 5.1. What do you say? Exercise 5.1. We're looking at A equals to BNF and let's see here, what's he say again? He says that's the upper triangular matrices. He says show that E1 is an eigenvector for A and find the corresponding weight and determine its weight space. Okay, so you know, what is AE1? This is column 1 of A. Excuse me, my bad. Let me not confuse the space with the elements, right? Bad form. Let M be an element of A. Then ME1 is equal to column 1 of A, right? Column 1 of M, rather. Right? And if B is upper triangular matrices, what does that look like? Yeah, the first column is just a multiple of E1 again, right? So it's something like, you know, alpha times E1, right? For some scalar.
Sorry, just a little ticky-tacky. It's example or exercise 5.2. Sorry.
Oh.
Just a little off.
Thank you. Ticky-tacky is the word for the day. But I will allow it. Let's see here. So, so it's an eigenvector of A, right? Because this was an arbitrary M. Arbitrary M, it's an eigenvector. And then the question is, find the corresponding weight and determine its weight space. Now, what's a weight?
It is the generalization of the families of all those maps, or like the eigenvector for all those maps, kind of.
Right, but it's the weight. Let's say it's lambda, right? So we need lambda, a mapping from, you know, A to F, right? Such that what? A of, well, in my current notation, M of V is equal to lambda of M, right? V for all m in A So I'm relatively certain that my weight here, lambda of m, we can just define it to be m11. This is a linear map, right? And I mean, what is alpha in this calculation, right? This is literally M11, right? I'm talking about the 1, 1 component of the matrix, yeah? So what else do I need to do here? Now the only v that works for, right? Let's see here how to say this. I think if we look at the v of this lambda, right? We're talking about v in well, in this case in Fn, I guess, right? Such that I'll use my current notation, m of v equals to lambda of m v for all m in A, you know? So for this to, and so by my definition, this is what? M11 v, right? So I haven't quite proved it, but I'm relatively sure that v lambda is going to be the span of E1. I mean, E1 can't be the eigenvector, you know, like you can't have E2. You can't have E2 in this. I mean, maybe I should call this like lambda 1 to be more, you know, helpful here. I feel like I should put a 1 on this, you know? It feels like this deserves a 1. It's the first weight. Find the corresponding weight and determine its weight space. I'm pretty sure the weight space is just the span of E1. Does this have an answer in the back? That'd be nice.
I do not think so. It usually has a little thingy if it does.
Aw, shnikes. Well,
we're at 5.3.
In fact, there are no answers to any problems in 5. It's funny. It goes straight from chapter 4 to chapter 6 in the back. All right, anyway, let us go on. So the next up, he talks about this invariance lemma, all right? I mean, his exercise 5.1 is interesting. He I feel like I think exercise 5.1 is still about the diagonal matrices. So if I can just kind of put some words with example 5, exercise 5.1, to put it into words is essentially to show that the dual basis to the standard basis give you the weights for the diagonal algebra. I wonder what happens here once you get to like past E1. All right, all in good time. So let's see here. Lemma 5.4. He says, suppose A is an ideal of Lie subalgebra L of GLV. All right. Let W equal to V and V such that A of V equal to 0 for all A and A. Then W is an L invariant subspace of V. All right, so here's the proof of that. We'll discover the meaning of some of these words as we go on in the proof, all right? So let W, little w, be an element of big W, and Y be an element of L. So I'm going to skip that little sentence right there. Consider AY, and this is like, Jacob, you'll remember this from quantum mechanics. AY is equal to YA plus the commutator of AY. I feel like that's the only calculation I ever do in quantum mechanics. Like this.
Is that not the commutator?
It is the, see, this is how to use the commutator to commute. Right? If you want to trade, I mean, this trick is like ubiquitous. It is everywhere. So to switch A to Y to A, you just have to add this at the correction term. And that really is where the term commutator comes from, in some sense, right? I mean, that's operationally how it goes. But he points out that if you look at that, the bracket of AY is actually an element of A, right? Since A ideal, right? And so what are we looking at then? Let's see here. Okay, well then we're not looking at anything yet. Thus, if we let the operator AY, well, excuse me, if we let A act on Y of W. Now keep in mind what's going on here. I know it's easy to get lost in the letters, but A is a mapping from V to V, right? And also y is a mapping from v to v, right? Now w is an element of v. W is a vector of this particular subspace we're defining to be the vectors in V which are annihilated by the operators in A. So this, I mean, I'm pretty sure that another notation for this might be like annihilator of A, perhaps. I mean, it's the set of vectors which are sent to 0 by everything in A. And so these are the things which A annihilates, I guess you could say. But I'm not sure that that's... What's that?
I remember your talk.
Oh, my talk. Which talk? I don't know if I remember.
Equation annihilators.
Oh, yes. Okay, so then this, we've got what? We've got y, a, w, plus the bracket of a, y with w, right? But what's the deal? This, by assumption, is 0. So y of 0 is 0, right? And again, this is in A, so this is also 0. So you get that that's 0, right? And what's that mean? Hence, QED, yeah, hence A.
YW is equal to 0.
YW is equal to 0 for all A and A, right? And what's that mean?
Yeah, that W is a set of annihilators.
Well, but that means specifically, that means that y of w is an element of w again, right? For all little w and w. Which is to say that w is an invariant subspace of y. See, when we're talking in linear algebra, we talk about invariant subspace. That means that when you take an operator and you act on the subspace, you get back to the subspace again, right? And what would it mean to be an invariant subspace, an L invariant subspace? Well, that means that for an arbitrary operator in L, it's an invariant subspace. That's what this calculation shows. It shows for an arbitrary operator in L, this W subspace is invariant. All right. Now, I guess I should mention, guys, let me talk a little bit about the backstory here about this, like the importance of invariant subspaces, because let me just talk about regular linear algebra for just a minute or two, just to try to add some value here. Can I erase? I think I can erase this, yeah. So if you have a linear operator, let's say T, which is a mapping from V to V, all right? And you have that V is the direct sum decomposition of, let's say, V sub I equals 1 to S. In other words, you've got like V1, direct sum V2, direct sum, Vs. So you have these S-fold components, all right? What that means is that these subspaces are independent. So if you look at the intersection of any any one of them with the sum of the rest of them, that's 0. In the case of 2, it just becomes the condition that the intersection is trivial and that they add together to give everything. But if you have 3 of them, you need that like the first intersected with the sum of the second and the third is 0. You need that the intersection of the second with the sum of the first and the third is 0. You need that the third intersected with the sum of the first and the second is 0. Otherwise, you could form a direct sum decomposition of the plane into 3 lines. See, 3 lines add together to give you the whole plane, and they intersect at the origin. But 3 lines do not a direct sum decomposition of the plane make. So it has to be, it has to be independence. Okay, so another way of there's 5 different ways of characterizing this. The one way is independence I was just telling you about. The other way is this holds if you can take a basis for each one of these guys separately and concatenate the basis and have the basis for the whole space. That's another way to characterize direct sum decomposition. Another way to characterize direct sum decomposition is that there exists a unique representation of each element of the algebra as a linear combination of vectors from each one of these different pieces, uniquely so. Another way to characterize direct sum decomposition is that there exists a unique representation of 0. That 0 can be written uniquely as the 0 in here plus the 0 in there plus the 0 in there all together. And that's the only way to form 0. That's another way. There's another way, which is that there's an isomorphism between this space and the Cartesian product of V1 with V2 with Vs. And that isomorphism is not just anything, it's the mapping that's simply formed by taking x1 plus x2 plus da-da-da plus xs and mapping it to x1 comma x2 comma da-da-da comma xs. These are the 5 equivalent characterizations of the direct sum decomposition. These things are in my linear algebra notes. They're also in like good linear algebra texts. Not the one you guys used. Sorry. Well, you used Anton, did you? This might be an Anton. Did you use Anton? Yeah, Anton's got some stuff in there. Anyway, okay, so that's the direct sum decomposition, all right? What is invariant subspace? Well, invariant subspace, right? If you have T of Vi is a subset of Vi, right, for all I, then that means that you have a very, you can expect that the matrix of T has a very special form. If beta you form as like beta 1, beta 2, beta s, right? Respectively the bases for these separate subspaces, all right? Then the matrix of T with respect to this basis is actually the direct sum of T restricted to beta 1. Well, let's say here, how can I say this elegantly? Let's say it's T, I need a new notation here, so let's say I'm going to say it's T1, direct sum with T2, direct sum with direct sum. And here I'm talking about the Kronecker product, Kronecker sum rather, which is just the, this is block, I'm saying block decomposition. So this looks like T1 matrix here, T2 the matrix here, TS matrix down here like that. And here, what I mean by TI is simply TI is the natural map. It is T restricted to VI, mapping to VI, which is a well-defined linear map by Y, by the invariance of T for each subspace, right? So if you can find a decomposition of your space, right, into a sum of subspaces for which the linear transformation is invariant, this is especially nice and useful because this gives you a block, a block diagonal decomposition of the matrix. The way this is often done is with Jordan. This is like an example of this would be the Jordan form. So the spaces, the V1 through Vs, would be the generalized eigenspaces. All right? And those will be independent. Like if you have distinct eigenvalues, the generalized eigenspace. So like, you know, Vi here could be something like, you know, let's say K lambda I, where we're talking about the null space of, you know, T minus lambda I to some power. Let me not be too careful about this. I'm going to put some quotes on here. There's some like delicate things that need to be done in terms of intersections and picking off what's called the highest weight eigenvector. See, because if your matrix is diagonalizable, then these V's you can just take to be lines basically in the direction of your eigenvectors. And you could have like, you know, well, for example, if you had 3 eigenvectors with eigenvalue 1, you could put those together. You could have a 3-dimensional eigenspace, right? Or you could have 3 1-by-1 blocks, each with 1. But maybe your matrix has like a generalized eigenvector of order, you know, 3, right? But you have lambda repeated 10 times. Maybe you have eigenvalue 3 repeated. Suppose you have eigenvalue 7 repeated 3 times, but you have the eigenvalue 7 with algebraic multiplicity 10 in your characteristic equation. Then you've got like at least one 3 chain, and you got 7 other vectors left over. Maybe they form some 2 chains. Maybe they just all eigenvectors. There's all kinds of different things that are possible. All right. But the point is to form the Jordan matrix. To form the Jordan form for the transformation, you can write the matrix as a sum of Jordan blocks, and actually find the blocks. You have to figure out what are the eigenvalues, what are their geometric versus algebraic multiplicity. Find the eigenvectors of highest weight; those generate the chains, and so forth. I think, roughly speaking, what's being tried to be done here as we go forward in the book is generalizing this idea, instead of doing it for one transformation, doing it for a whole algebra of transformations. So you don't just have one matrix, you've got a family of weights. But there are similarities in the concept. So anyway, I think it's important for you guys to hear about this, because as you use grown-up applications of linear algebra, like this is really, really important, the direct sum decomposition. Anyway. Questions, Audrey?
Makes a lot of stuff from our hyperbolic analysis make a lot more sense.
Well, good. All right, so next up is the invariance lemma, which I will state over here. Ah, it's hideous. Come on, come up there. LLE subalgebra of GLV, A an ideal. So, Jacob, I'm going to try to get to more interesting stuff today, because I don't want to just do technical things. I want to tell you guys some big theorems here today, too, you know. GLV and A and ideal. So I will get to it, I promise. And I will do that by skipping some proofs. A and ideal of L. All right, then we have lambda be... I'm just turning into physicists. It's probably true. A weight be a weight of A. What's that mean? I think we've done enough that we have some appreciation for that, right? A weight of A. The associated weight space V lambda V and V, so it's the usual definition, okay, such that AV is equal to lambda of AV for all A and A. is an L invariant subspace of V. Now, the proof of this is beautiful. It's like a page. It involves some, it's got an inductive, it's got an abstract induction argument in there. It involves a really clever construction of U that builds in a certain linear independence into the set that you use. It's a very cool proof. It's very cool. I want to just try to understand for a second, what are we saying? What are we saying? L is a Lie subalgebra of GLV. A is an ideal of L. Lambda weight. It's an L invariant. So that means that V lambda is an invariant subspace of everything in L, right? So what we're getting at here is being able to simultaneously diagonalize like the totality of L with the same subset. See, that's what that is up against. That's what the idea is, right? Is you're like, okay, well, this is just, there's no simultaneous diagonalization over here, right? But if you have more than one T, right? And they both share the same invariant subspace V1, then when you build the basis with respect to this decomposition, and you look at the matrix for a T and another one, let's say S, they have the same kind of block decomposition. And so when you multiply two such matrices, the blocks stay on the blocks. The blocks interact with the blocks. Like there's something to be, and the most dramatic example of this is when the blocks are all one by one, in which case you've actually like simultaneously diagonalized the two operators. But this is better than simultaneous diagonalization because it doesn't have to quite be that. It's simultaneous blocketization. That's what's going on here. It's simultaneous blocketization. That's what's the idea here.
I understood it as like if you took that V lambda is the space of all these operators that are invariant. Like everything in V lambda is essentially an operator that keeps this that working on acting on L is invariant.
Well, but V lambda is a subset of V. In terms of the application to physics, that's the representation space. It's the space on which these operators are acting. So, A might be a physical.
So we can't call elements of it operators.
Yeah, I think of V as like static. It's a given vector space, whereas the A is being taken from this subalgebra of GLV. And, well, it's okay technically from an ideal. So. Oh, yeah.
But going back to the definition of weight.
Yeah.
We have lambda is a mapping from the subalgebra to the field.
Yeah. Right.
And so we're taking all possible mappings and calling that a subspace.
All possible mappings and calling that a subspace. Well, let's say this. The dual space of A is a linear space. And every vector in there is a weight. No, excuse me, not, okay, I gotta be more careful. The dual space is a vector space. Some of the dual vectors are weights, but not all of them. Because in order to be a weight, I believe V lambda has to be non-trivial.
So
Isn't that right? Didn't it have to be non-trivial?
Non-zero
the
subspace.
dual space
Non-zero
has
sub.
vectors that are weights.
So you see, Audric, in the vast majority of dual vectors that I pick, this V lambda thing will just be 0.
But
On,
the
on,
weight space is the space of all these lambdas in the dual space, or all the vectors in the dual space that are weights. So
well, I guess that could be that's probably going to be like a finite set, right?
well, my question is the weight space now all vectors in the dual that are weights?
I believe so. And I think that's not going to be a vector space. I think that's going to be like a,
If it's a subspace. Oh, wait, is the weight space a subspace? I don't know if I might be mixing it up. No, yeah, it says it's a.
Yeah, so it's not your subspace.
where does it say that?
It's an L-invariant subspace of V.
Where are we?
So it might not be.
Well, where are you?
Last sentence of that, like the boss of the definition 5.3, page 39.
Oh, okay. But that's not. Is this called the weight space?
You say the vector space.
That V lambda is the weight space.
Oh, that's the weight space. Oh, okay.
Yeah, if you go to the definition.
True. Now, okay, but that that is okay, great. If that's the weight space, if they've called it the weight space, it's the weight space. We can't escape it, right? They have named names. We're stuck with it. But I would point out that the set which contains the weights is not the weight space.
Yeah.
Okay.
The set which contains the weights is
That V sub lambda is the weight space. But
for lambda.
the weights satisfy that condition of those V in the vector space V. This is the AV. Yeah.
The set that contains the weights is not the weight space.
Yes. Because V sub lambda is the weight space.
A weight is a dual vector. V lambda is a subset of V, so it can't be the same thing. Like V sub lambda is a subset of the vector space V. A weight is a dual vector to V.
V lambda is called the weight space, but it's not the set of all the weights lambdas.
Yeah.
Lambdas. Right?
I believe so. Now, I could be. I need to.
There's something technical that I'm just trying to understand the definition better.
Yeah, sure.
But yeah,
So-
it's like we have this thing called the weight space, but it's not like intuitive what it is. It's like
Right.
well, it's not the set of all weights in the dual. No, it's the set of all vectors such that you get
Yeah.
you have AV equals.
Let's see here. I wonder if section 5.4 helps any at all. I don't know. It's proposition 5.7. Let X and Y be linear maps from a complex vector space V to itself. Suppose that X and Y both commute with the commutator of X and Y. Then the commutator of X and Y is a nilpotent map. So he. I don't know. I think I'm going to skip that for now. Well, probably forever, but I'm going to go past section 5.4. I think we talk about weights more later, Audric, and I think it'll make more sense when we do. Like, if I remember right, let me see if I can find it.
Like intuitively, what I thought it was eigenvectors. You take a family of all these linear maps, and you're like, okay, all of these have some type of generalized eigenvector because they're very close together, and that's a weight. If you take the set of all weights, that's the weight space, but that's not quite right. It's actually